Hi students. In the last video, we were studied about the application of Kirchhoff's laws. That is, first application, Firststone's meter bridge. In this application, we were studied about construction of meter bridge, working of meter bridge, and we formulate the formula for the measurement of unknown resistance using meter bridge instrument in which Firststone's network's balancing condition is applied. And if we formalize that formula using meter bridge, then in the use of Firststone's meter bridge, some errors are produced. These errors are occurs in the measurement of unknown resistance, so it has some source of errors in the measurement of unknown resistance. Source of errors, in which first error is the cross section of wire may not be uniform. Means if we use a 1 meter length wire in the meter bridge having not same cross sectional area, then resistance per unit length of wire may not be uniform. That's why error is produced in the measurement of unknown resistance using meter bridge. After that, the second error is the ends of the wire are soldered to the metallic strip where contact resistance is developed, which is not taken into account. That is, a wire used in Firststone's meter bridge having length 1 meter and which are fixed on rectangular wooden board between two thick L-shaped metal strips. Means wire is fixed on two L-shaped metal strip. At the ends of this wire, a contact resistances are developed, and this contact resistance also affects the flow of electric current in Firststone's meter bridge, but this resistance are not taken into account in the measurement of unknown resistance X using meter bridge. That's why there is error is produced in the measurement of unknown resistance. After that, the third error is the measurement of Lx and Lr may not be accurate because the ends of wire not match the values of 0 and 100 on the meter scale exactly. That's why Lx plus Ly or Lx plus Lr is not equal to 100, which causes error in the measurement of unknown resistance using meter bridge. These are some sources which produces error in the measurement of unknown resistance using meter bridge. So these errors occurs in the measurement of unknown resistance using meter bridge, which having some minimization, means some factors taken into account, then errors are minimized. These factors or minimization of the errors are as follows. First minimization is the value of R is so adjusted that null point is obtained to middle one third of wire, so that percentage error in the measurement of Lx and Lr are minimum and nearly the same. Means If we take the resistance from resistance box having adjusted value such that a balance point or a null point is obtained at middle one third of the wire using in Wheatstone's meter bridge, which causes minimization in the percentage error in the measurement of lengths of null point from ends of the wire A and B. So this is the first minimization in the measurement of unknown resistance using meter bridge. After that, the second minimization is the experiment is repeated again and again. Means experiment is repeated by interchanging the position of unknown resistance X and known resistance box, that is R. For the minimization of errors produced due to contact resistances, we repeat the experiment again and again by interchanging the position of unknown resistance and known resistance box. This causes error which occur due to contact resistance. This minimizes error occurring due to contact resistances. And third minimization, the jockey should be tapped on the wire and not slided. We use jockey to get the null point, and if we not slide the jockey along wire AB, then there is minimization in the error which is produced in the measurement of unknown resistance. These are the some minimizations which are produced in the measurement of unknown resistance using meter bridge. After that, we see applications of a Wheatstone's meter bridge. We know that Wheatstone's meter bridge is used for the measurement of unknown resistance, and this instrument is used for measuring the value of very low resistance precisely. That is, for the measurement of very low resistance correctly or accurately, you use such an instrument, that is Wheatstone's meter bridge instrument. With the help of Wheatstone's meter bridge instrument, we use with the help of Wheatstone's meter bridge instrument, we measure or we calculate a resistance having very low value accurately. After that, the second application is we can also measure the quantities such as galvanometer resistance, capacitance, inductance and impedance using such a instrument. That's why Wheatstone's meter bridge is very useful instrument in the measurement of resistance having very low value precisely and accurately, as well as it is also used for the measurement of galvanometer resistance, capacitance, inductance and impedance also. Students, do you know that Wheatstone's bridge or meter bridge along with operational amplifier is used to measure the physical parameters like temperature, strain, etc. Also, students, Wheatstone's meter bridge is also used for the measurement of physical parameters like temperature, strain with the help of operational amplifier. If Wheatstone's meter bridge is used along with operational amplifier, then we can easily find out the physical parameters, or we can easily measure the physical parameters like temperature, strain, etc. Students, after that, or after seeing Wheatstone's meter bridge, we see the Kelvin's method. Kelvin's method, which is designed by scientist Kelvin to determine the resistance of galvanometer using meter bridge. That is one of the application of meter bridge, or meter bridge instrument is used by Kelvin to determine the unknown resistance, which is the resistance of galvanometer. So Kelvin's method to determine resistance of galvanometer, denoted as symbol capital G, using meter bridge. So that is the circuit diagram of Kelvin's method. By seeing that circuit diagram, using that circuit diagram of Kelvin's method, we explain the construction of Kelvin's method to determine the resistance of galvanometer G with the help of meter bridge. So in Kelvin's method, we use a metal wire which is having uniform cross-sectional area made up from metal with length 1 meter is fixed on rectangular wooden board with the help of two thick L-shaped metal strips. And a third metal strip, central metal strip, is mounted on wooden board which makes two gap with that two thick L-shaped metal strip, in which in the left gap, that is gap between L-shaped metal strip and central metal strip, a galvanometer is connected. That is, and in the right gap, a known resistance means resistance box is connected. Below that metal wire AC, a meter scale is fixed and along wire AC, a source of EMF E, plug key K and rheostat RH are connected in series. And a jockey which is connected directly on the central metal strip B, which is used for obtaining the balancing point D, which can slide along wire AC to find out the balancing point. So that is the construction of Kelvin's method to determine resistance of galvanometer G by using meter bridge. The construction of Kelvin's method is same as that of construction of meter bridge, but only difference is that in place of unknown resistance X, we use the galvanometer and jockey is directly connected on the central metal strip, that is metal strip B. That is the only difference between Kelvin's method and meter bridge. Using that construction, how to calculate the resistance of galvanometer using meter bridge, that is working of galvanometer, working of Kelvin's method to determine the resistance of galvanometer. First, a suitable resistance is taken in the resistance box and current is sent throughout the circuit by closing the key K. After that, without touching the jockey, at any point of wire AC, we see the deflection in the galvanometer. And note down that deflection, that is the deflection before touching the jockey at any one point of wire AC. After that, the rheostat is adjusted to get the deflection around middle one third of the metal wire AC, that is around two-third range, two-third of range. Now the jockey is strapped or jockey is placed at different points of wire AC. Then we get a point D, which is the point of contact at which galvanometer shows no change in the deflection which is found before without touching the jockey. Deflection we get without touching the jockey is again get by touching the jockey by taking suitable value of resistance from resistance box. As the galvanometer shows the same deflection with or without touching the jockey at points of wire AB. Then between the point B and D, these 2 points must be equipotential points. Point B and point D having same potential. Point B, point D having same potential means these 2 points are the equipotential points. So there is no flow of electric current from B to D and circuit is balances. At the condition, if circuit is balances, then we measure the length of bridge wire between the point D and point A, that is the left end of the wire is measured as LG, and the length between point D and C, that is the right end of the wire and balance point D, considered as LR. LG, that is the length between point A and balance point D, and LR, that is the length between balance point D and end C of wire AC. That is the working of Kelvin's method, which is used to determine the resistance of galvanometer by using meter bridge. Then how to calculate the resistance of galvanometer using meter bridge? Let RAD, that is the resistance across wire AD, and RDC is the resistance across wire CD or DC respectively, since bridge is balanced. If bridge is balanced, then resistance across wire AD is RAD and resistance across wire DC is RDC. Then we use the balancing condition which is obtained in Wheatstone's network, that is first resistance upon second resistance is equal to third resistance upon fourth resistance, that is G upon R is equal to RAD upon RDC, where G is the resistance of galvanometer, R is the resistance which is taken from the resistance box, which is the known resistance, RAD is the resistance across wire AD, and RDC is the resistance across wire CD. But RAD is considered as sigma Lg, and RDC is considered as sigma Lr, where sigma is the resistance per unit length of the wire, which is having same value because wire used in this instrument having uniform cross sectional area. Therefore, RAD upon RDC is equal to Lg upon Lr. Therefore, above equation become G upon R is equal to Lg upon Lr, in which R having known value, Lg which is measured value, length, balancing length between point A and D, Lr that is balancing length between points D and C. That's why these three values R, Lg and Lr are known values, and using that balancing condition with equation G upon R is equal to Lg upon Lr, we can easily find out the resistance of galvanometer G using Kelvin's method. And another formula for the resistance of galvanometer, that is G is equal to Lg upon 100 minus Lg into R. Using this formula, the unknown resistance of the galvanometer can be calculated. After that, another application of Fitstone's meter bridge, that is post office box. A post office box is a practical form of Fitstone's meter bridge as shown in the figure. The resistance in the arms P and Q are fixed to desired ratio. The resistance in the arm R is adjusted so that galvanometer shows no deflection. Now the bridge is balanced. The unknown resistance X is equal to RQ upon P, where P and Q are the fixed resistance in the ratio arms and R is an adjustable known resistance. If L is the length of wire and R is its radius, then specific resistance rho of the material of the wire is given by rho is equal to X pi r square upon L, where pi r square is the area of cross section A. So students, we see the application of Kirchhoff's laws. First application, meter bridge. In this video, we studied about errors produced in the measurement of unknown resistance X and minimization of that errors, as well as application of meter bridge and Kelvin's method to determine the resistance of galvanometer. Remaining part of this chapter will studied in our next video. Thank you.